Hello IB. We're now moving into chapter 17 where we do all these applications, real-world applications to differential calculus. So chapter 16 was looking at graphing and functions and be able to describe the functions using calculus. Now these are the real-world applications. The three areas we're going to look at are kinematics, which is all to do with the movement of objects, just general rates of change, so they could use that in production, and that's related to optimization, where, so if you're running a factory, what's the rate of change of production with different changes on sort of input of materials, resources, human labour? How do you optimize your production? How do you optimize areas? How do you optimize sort of anything to do with optimization that you can model with a function, and you can apply your calculus in that area. So we're going to look at kinematics in these next two, in chapter 17a. We'll break the video into two parts because it's quite a major part, and you will certainly find these sort of questions in your IB papers later, not that we're just teaching to the IB exam. So the basic problem that we're starting with is for Michael, someone riding their bike, and you've plotted the data. So you probably would have remembered from your year 10 where you looked at motion graphs and you had things with straight lines, and we'd often talk about that going, well, in reality it's not a straight line. You don't instantaneously start at a speed and instantaneously stop. It'll be curved. So that's what we see here. And that means we can model it not with a piecewise linear graph, but with a continuous graph, like in this case, we've got it described as a cubic function. So our movement is looking like a cubic function. So the dots on the graph showing Michael's position. So this is his position from leaving home, going up the hill and then down the other side of the hill. So we could do a straight line graph at t equals 0. So this could be just like an x-axis, where here is the distance. And note, we're using s as a function of t for his distance. So s does not mean speed, it's meaning distance, or in this case, displacement. So s as a function of time, where he is. Graphing that out, and we can model it with this cubic equation. And we're looking at a restricted domain of t between 0 and 19 minutes. Note, in any of your kinematics, your time is always going to be greater than or equal to 0. We don't talk negative time unless you try to predict where they were before, but generally time is equal to 0. Your graph starts here. And so in this example, we want to look at why is this an increasing function, so the concept of increasing. We've talked about before, why is it always going up? And that's because he's going further away from his house to his friend's house. Can you find a function for Michael's speed at any particular time t? So in other words, how fast is he going? Remember, speed is your rate of change of distance, or the change of distance on time. So write down speed at any time. So this is the rate of change. Rate. Let's just try that again. We'll pause that for a moment. All right, so it's a change of distance over time. So we're looking at, in this case, the gradients of the curve at any particular time. I'm not going to go into the answers because you'll come across this question in the exercises. So we can look at the slope of the graph, and if we're ever looking at the slope of a tangent or a slope of a curve at a time, we're looking at our calculus, we're looking at differentiation. The acceleration is the rate at which his speed is changing. So how much of the gradients of these at each time are they changing with respect to time? So we can interpret that as our second derivative. So this was our first derivative, getting our speed, s dash of t. And our second derivative is looking at how much his speed is getting faster or slower. Whereas the velocity is looking at the change of distance over time. So basically here you're trying to find his speed and acceleration at the time 15 minutes. So in other words, you're trying to find the first derivative at 15. And then the second derivative, what's his acceleration at that time? Is his speed getting greater or slower? At what time do you think the hill was the steepest? How far had Michael travelled at this point? If it's the steepest, then he's probably going the slowest. In other words, when's the slowest gradient of the tangent? What's his slowest speed? And having looked at, in chapter 16, points of inflection, you're probably going to find that at time 10, looks like it's a point of inflection. And so a horizontal point of inflection. So that could be when he gets to the top of the hill, or he's almost zero, and then he starts to go down. So that looks like it could be the slowest time he's at. But it's always going to be positive, so the slowest will be at 0. So anyway, you can look at that one in more detail later. So let's go through this in greater detail now. In the kinematics that we're doing, we're only going to be looking at a particle moving in one dimension, like going one direction. So we're going backwards and forwards in, say, horizontally, or we're going up and down. So a particle, a bit of a funny line. So we're not looking at three-dimensional movement. So in this case, remember I mentioned earlier, we're using S as a function of t as displacement. That's our displacement function. And that gives the displacement of a point from the origin at a particular time t. And again, t is always greater than or equal to 0. So if S is greater than, if our displacement is greater than 0, that means the point lies to the right or is in the positive. So it's either in this positive region, all right, or it's up. Point lies to the right, or we can go or up, right? It's in the positive section of your graph. If it's equal, if our displacement is equal to 0, it means it's at the origin. Which will be here, or in this case, if that's our origin. And up is positive, so 2, 4, 6, 8, let's make that 10. 2, 4, 6, 8, there'll be minus 10 here. So if our displacement is less than 0, so then our point, particle, person, whatever we're looking at, lies to the left. Or down. All right, so remember displacement is where you are on your set of axes, whereas distance travelled is talking about how far you've travelled. Or how far you've moved. This displacement is a vector. So we're going to keep using that term more and more. We'll do a whole topic on vectors shortly. A vector has magnitude, it's got some number, and it has direction. Whereas the distance travelled is a scalar, which means it only has magnitude and that means it can be only positive. Whereas our displacement, because it has magnitude and direction, it can be positive or negative. So let's look at another example now. So let's say we've got some particle that's moving according to this rule, this equation. S is equal to t squared plus 2t minus 3. So that means the particle, we can, let's just put a dot there, we want to select that. So here's the function and here's our point. So it's moving in a straight line like that. Now that's quite hard to see. We can see it's getting faster at the end, but like it's hard to see much more. It helps when we plot it out on a XY plane. So it was looking like it was going slower here and then gets faster at the end. So let's have a look at what that graph would look like. This is a nice simple one, so that means you can factorize it. Always check to see if you can factorize, and we've got t equals to, what we've got, plus 3 t minus 1, which means we've got zeros when our function is when our displacement is equal to 0. It happens at time minus 3 equal to 0. Then we've got t equals minus 3 or plus 1. Are we going to take t equal to minus 3? No, because we want t greater than or equal to 0. So at plus 1, it's at the origin. So that means here, it's at the origin here at time equal to 1. If we plot this where we've got, let me go back and label our axes. If this is our time and up here is our displacement, then we can plot that and have a look at it. So here we go. This is what it looks like with our time and displacement. There we are at 1, it's at 0. So this is how far it is from the origin. So it means at time equal to 0, it's actually at, when t is equal to 0, we can see it's at, make a pin there, right, at minus 3 from our equation. So here, it's at this point, at t equal to at t equals 0. So we can go through and work out either from the graph or algebraically. T, we've got that is equal to minus 3. At 1, s of 1 is equal to 0. So we can go through and work out each of those values to see whereabouts it is, or we can just read them off the graph. So let me fill that in for you. All right, so we've got these other points. It's at 5 when t is equal to 2, and it's now at 12 at t equal to 3. So we can certainly see from this it's going faster. Here it's getting faster and faster, and it obviously will keep getting faster. We can see that also from this graph here, where the gradient, the tangents, are always positive, and they're getting steeper and steeper as you go along. So we can either graph it on that two-dimensional axis with displacement against time, or on this single axis and come up with a motion graph. So this is what's we call the motion graph. And both of these are useful tools for helping us understand how the particle or the point or the person is moving. So summarising these main terms that we need to know, apart from displacement and distance travelled, we've got velocity. So average velocity is for an object moving in a straight line from an interval t equal to 1 to t equal to 2. In this case, remember, if it's an average, we're talking about the ratio of the change in displacement over the time taken. This is what you would have done in up to year 10, where you get the final position minus the initial position. That's another way of thinking about it. Final position, initial position, over the change of time. If it's a velocity, we're talking a vector. So again, we're talking magnitude and direction. So this is a vector. Whereas if we're talking speed, we're talking a scalar, just magnitude. So our speed is going to be our distance travelled, or just overall how far we've travelled. Over the time taken. Alright, so that will only ever be positive, and whereas here with the velocity vector, the average velocity is going to be the positive or negative depending on which way we're going. Instantaneous velocity is going to be where that whole concept of calculus, where we want to come down to a small change in time, so this is our small change in time, and we do that calculus from first principles, but we'll always use our rules. So small change in time. So at velocity, again, because it's velocity, we're talking, it's a vector, which I've got written straight below there. So whenever we talk velocity, we're talking vector, magnitude and direction. So we can take the first derivative of our displacement function to give us our velocity function. So if this is a vector, if our velocity as a function of time is positive, it means we're moving to the right. Our change of displacement is going to be in the positive direction. Whereas if our velocity is negative, it means we're moving to the left. And probably just to clarify, if our got a bit messy. If our velocity is 0, it means we're stationary, we're not moving, and that's hopefully obvious. Speed is a scalar, so always positive. So it doesn't tell us where we're going, it just tells us how fast we're going. So average acceleration, this is the change of velocity. So again, we're looking at that average. So because velocity is a vector, then acceleration is going to be a vector as well. So it's like a general concept. So let's say our velocity graph looked like this. If this is our velocity, and that's our time. If we're doing an average, we're just taking it from one time to another time. Whereas if we're doing instantaneous, we're taking a tangent to the curve. So it gives us more accurate information. So our second derivative, using our calculus, will give us the instantaneous acceleration. So in other words, as we start with our displacement, if we differentiate, then we get to our first derivative, and that's our velocity. And then if we do our second derivative, that's meant to be over here. So if we do our second derivative, differentiate again, we get our second derivative, which is our acceleration. And later we'll find, when we come back to our calculus, when we do integration, that takes us back from acceleration to velocity, and then we can integrate back again to get to our displacement. For units are really important in this topic. Our displacement could be, say, meters. Our velocity will be meters, say, per second or kilometers per hour. And then acceleration is going to be meters per second, which is meters per second squared 4 metres s to the minus 2. All right, so always think about your units when you come to do this section. All right, this is getting a long video because this is a big component. So question 17A.1 I just want to quickly talk about, and then I'll put those up in the notes for you. But here we've got our function that describing our displacement. And if we factorise that, we won't be able to factorise that. Minus 2 plus 1. No, we can't factorise that. So you need to use your calculators for that. We could find the average velocity. So remember, your average velocity is just your, move that over a bit. Average velocity. Always check whether it's average or instantaneous. Is going to be your final displacement. So at 3 minus your initial displacement at 1 over the change of time. Alright, so you can just substitute that in to find those values. In part B, you're asked the average velocity from t equal to 1 to t equal to 1 plus h. So here they're taking you through the steps to do it basically from first principles. So in this case, your average velocity will be the displacement at 1 plus t, 1 plus h, the final, minus the displacement at time 1. You're going to need to substitute that in, 1 plus h, and do all the expansion. And you come down the bottom, the change of time will be 1 plus h minus 1. So you come down to a value there, and when you work through it, you actually get down to equal to h plus 5. Oops. Just come over here, bit of space. You then look in here, find the value of that as you take the limit, which is obviously our instantaneous velocity, is going to be your limit as h approaches 0 of your h plus 5, which is going to be 5. So we're talking metres and we're talking seconds. So our instantaneous velocity at time 1 was 5 metres per second. We could have, of course, done that by just doing, what have we got? Our displacement function is t squared plus 3t minus 2. So our first derivative is going to be 2t plus 3. So at time equal to 1, we're going to have, oops, tidy it up, 2 times 1 plus 3, 5 meters per second. So that's how, the question doesn't ask that, but that's basically what we would be doing, because you won't be doing it all from first principles. And so part D, find the average velocity from time t to t plus h, you're basically doing, you're going to come down to 2t plus 3 when you do that calculation. So for part D, that's where you'll come down to once you take your limit. So that's part 3, and then you can substitute in for any time. So let's leave it there, and I'll do another video that covers the second part of this section. Thanks for listening, and hope the things are clear for you.